In this video, I'll cover what we call the natural response of RC circuits. And natural response happens when some sort of a capacitor stays in A for a very long time, so it gets charged. So what happens is at time zero, we actually move from A to B, and we end up with this particular circuit, which just contains the capacitor and the resistor in here. This is R and this is C. So we call this the natural response, or maybe zero input response, or maybe source-free response, because it doesn't have any voltage or current source in this particular case, and the capacitor has some sort of a charge, and it naturally releases that energy that it stores into R. And so in this video, I'll just focus on this particular case only, and I'll try to figure out what the voltage across, actually it's the voltage across both of them. It's actually the voltage between this one in here, VC of t, and this one here is just simply VR of t. And of course, both of them are the same voltage because they're technically in parallel. They share the same voltage. All right, so the way we're going to do it is the following. I'm just going to assume that we have some sort of a current in here that will be IC of t, and of course it is the same current flowing through IR of t in here. So what I can do is I can just simply say, well, I will tell you that IC of t is just simply equals to IR of t. Okay, that's the equation. But we know IC of t is just simply C times dVt divided by dt, but what I need you to pay attention to is this particular current in here. This particular current is going to the negative of the capacitor, and I'm now writing the capacitor current, okay? So the current is going to the negative, so what I need to do is I need to put a negative in here, okay? And that equals in here, and the current actually in here, if you think about it in terms of VR, it's actually going to the positive side, so it will be just simply positive VR of t divided by R. And of course it is the same V, so I'm not going to say VR or VC because they're exactly the same V, and I'm going to just basically say between here and here what I'm interested in is that V of t in here. So now I'm just going to do a little bit of algebra just to rearrange the terms, and what I'll end up with is the following: dV of t divided by d of t, and I believe if we move to the other side, that will be C, and that will be plus, I think, V of t divided by R equals 0. And if I actually say dV of t divided by d of t plus 1 over RC V of t equals 0. So this particular equation is the first order differential equation that describes the natural response of an RC circuit. And this is of the form here. So this is basically dx of t divided by d of t plus 1 over tau x of t, and in this particular constant it just happened to be 0. So what I want you to pay attention to is that now tau is actually the time constant, is just simply RC, and its unit is usually in seconds, okay? And the reason why we need it in seconds is because what we need, we'll find it shortly, that the solution will have some sort of an e to the negative t divided by tau, and we need that e to have unitless exponent. Anyway, so this is basically the first order differential equation, so you can solve it the way you're comfortable with it. I'll just basically solve it with the most simplest case, which is, let me isolate the v and the dv to one side and the t to the other side. So the way I'm going to do it is with a little bit of algebra. I'll end up with the following: dv of t divided by d of t equals negative 1 divided by RC v of t. Okay, and that means dv of t divided by v of t, okay, equals negative 1 divided by RC of d of t. Okay, if we take the integral for both sides, so that will be d, instead of v of t, I'm going to say y divided by y in here, and that will be v of t0 all the way to v of t, and that will be negative 1 divided by RC, and that will be from t0 to t, and that's basically d of x. So we do the integrals in here, and what we'll end up with is this is the natural logarithm of v of t divided by v of t0 equals negative 1 RCt minus t0. And for the sake of simplicity, let's assume that t0 is just simply 0, because in this particular case in here, if you think about it, that is our initial one. We decided that at t0 we actually flipped the switch. Okay, so if t0 is 0, that will simplify the equation a little bit, so that will become the logarithm of, or natural log of v of t, v0 in here equals negative 1 over RC of t. Okay, now if we take the exponent for both sides, we'll end up with v of t divided by v0 equals e to the negative 1 divided by RC of t. Okay, and now we do v of t, which is the solution, is just simply v0 e to the negative 1 RCt. But if you think about what v0 is, it's basically the initial voltage across the capacitor. If you think about it in here, the initial voltage across this capacitor before t is 0, remember it's like it was connected to that, it's just simply Vs. So in this particular circuit, for this particular case, you can either call it V0 or you can just basically substitute with the value of Vs. Either way is fine. But the interesting thing about it in here is now I have a solution that's V of t equals V0. I'll just call it V0 or Vs, e to the negative 1 divided by tau of t. And that's basically the solution of the shape of the following shape. Let me just highlight it here. So this is basically the solution, and this solution is of the shape basically x of t is just simply some sort of an x of t 0, e to the negative t divided by tau. That's what we have in here. Okay, and instead of x of t of 0, we can basically just say, well, this is of the shape c1, it just happened to be 0, plus c2 e to the negative tau divided by t. So it's important to emphasize the following in here. So the equation we found in here is just simply v0 e to the negative t divided by tau is actually for t is greater than or equal to 0. So let me just, the important thing that I want to focus on is this equality in here, that it's greater than or equal to 0. And the reason why is what we have in here is we have a capacitor and we have a resistor. That's the equation for this particular circuit. Okay, and I'm saying it's greater than or equal to 0 because at 0, actually the voltage across the capacitor cannot change instantaneously. So before 0 it was that, and after 0 it will be the same exact thing. So at 0 it just happened to be V of s because it cannot change instantaneously. So if I'm plotting this, what I'll end up with is the following. At 0 we'll have that V of s or V of 0, okay, and then it will exponentially go all the way to 0 in here. That's what we have in terms of Vc of t. Okay, so that the voltage across that capacitor cannot, basically it wasn't 0 before, it was V of s. That's what it was before 0. It was V of s and naturally went down. There's no jump in here and the equality is fine. At t0 it was V of s. Now let's think about it in this way now. So what I'm interested in now is if this is Vc of t, okay, or V of t, okay, let me just call it V of t because this is what we called it. Okay, so this is V of t. And let me just figure out what IC of t is, which is the same as IR of t, okay? So we know that I of t, okay, is simply C times dV of t divided by dt. So all we have to do is just take the derivative of this equation in here to just figure out what the current flowing through the capacitor and resistors are, okay? So that will be just simply C, let me just write it in here, C times negative 1 divided by tau or RC. Tau is the same as RC, okay? E to the negative, well, we have V0 in here, e to the negative t divided by tau, okay? And I believe that will be it. And in terms of passive sign convention, well, we have a negative in here, we have a positive in here. So the IC of t, we have to put negative in here, we have to put negative in here. So that will give us basically V0 divided by R, e to the negative t divided by tau or RC. Like I can either write tau or RC because for RC circuits is just simply RC in here. Okay, and I believe that will, yeah, that will be it. So that's I of t. So it's important to emphasize the following. This equation in here is correct for t is greater than 0, not greater than or equal to, it's greater than 0. Because let's think about it. When the switch was here for a very long time, the current through that capacitor was 0. And when we switch to the other side, the current is not 0 anymore because there will be some sort of a current flipping between for R. So if I'm to plot this in red, so if I'm basically say that I of t is in red, you will see that before 0 it was exactly 0, and after 0 there's like a big jump, and then it will actually decay somehow all the way to 0 again. Okay, that's what it will be. Actually, let me just make sure I plot it correctly because that will be V of s divided by R. It will be similar here. Is Vs divided by R, okay, and it will be 0. So it's a different it's a different point that it will range to. But what I want you to pay attention to is at 0, what we have is we have two values. We have I of 0 minus is just simply 0, and I of 0 plus, basically right after 0 is just simply V0 divided by R, because if you substitute the t equals 0 in here, that's what you will get. So there are basically two different values in here. Okay, so we have 0 before and 0 or V0 divided by R afterwards. And of course you can go ahead and just, if you were interested in computing the power is just simply of either one of them. So let's assume that you want the power at C or the power at R. Either way is fine. So let's assume that I'm interested in P of C, T, okay? And that will basically tell me it's negative I T times V of t, and then negative because I have the current is actually going to the negative side in here, so passive sign convention tells me that you have to put negative, so that tells me it's negative. Well, what is I of t? I of t is just simply V0 divided by R e to the negative t divided by RC. Okay, there should be a negative in here. And then what we have in here is we have to multiply it, let me just do this here, we have to multiply it by the V0 e to the negative t divided by RC. Okay, and that simply is just negative V0 squared divided by R e to the negative 2 t divided by RC. Okay, and that's basically the power provided the power provided by that capacitor. Why is it provided? Because V0 squared is positive, R is positive, this one is positive, so it's negative. So, and we know that basically the capacitor will have a negative power because it will basically be not generating but releasing power. And if you compute the same thing at the R, you should end up with the same solution, just with a positive in here. And of course, this is for t is greater than 0, exactly greater than 0, because again, PC of 0 minus was just simply 0, because it wasn't, there's no current flowing through the capacitor before 0, and PC of 0 plus will be just simply, well, we can compute that. Well, if t is 0, the whole thing here is 1, so that will tell me basically it's negative V0 squared divided by R. So they're different. There will be a jump. It's okay for power to jump. It's okay for the current to jump across the capacitor, but not the voltage. So to summarize, what we end up with, natural response of RC circuits, we call them RC because we have a resistor and a capacitor, one capacitor and one resistor, or one equivalent capacitor and one equivalent resistor. We'll end up with this particular differential equation to describe this particular circuit, and the solution for it is the following. This is V of t. What we have is some sort of an initial voltage across that capacitor, and that initial voltage will just decay based on some sort of a value of RC. So tau happened to be now we know that the time constant for an RC circuit is just simply RC, and its unit is in seconds. And the reason why we need the unit in seconds is because we need this to be unitless. So the time is in second, the RC has to be in second. So this will be in ohm, this will be in farads. So just make sure the units actually are in ohms and farads. And in here, okay, and the current, of course, the current across that capacitor in here is just simply V0 divided by R and to the same e to the negative t divided by RC. This one here is t is greater than or equal to 0 because before 0 and after 0, and at 0 the Vt doesn't change instantaneously because it's a capacitor, but before 0 the current was 0 and after 0 the current is this way, so at 0 there's a little bit of a jump. So what I'm saying in here, if you ended up trying to find the solution for a natural response of an RC circuit, what you need to do is you need to find the following. Find basically the initial voltage V0 across the capacitor, find tau, which is just simply RC, and then just basically take these and substitute in these two equations, and you'll be able to figure out the voltage and the current through the capacitors or the resistor.